Hello there, I'm Markku-Juhani Saarinen. I'm with PQShield in Oxford, England. This talk, we do post-quantum crypto, but this is a very generic talk about crypto implementation on RISC-V, and specifically about the now ratified, or 1 year ago, ratified extension Zkt, which is the time-independent or data-independent latency extension on RISC-V. And this is how one can test basically your code that it is so-called constant time unquote on RISC-V that hardware that implements this extension. I've been a cryptographer since the 90s, and for most of that time we've had these timing attacks. So here's like a very brief history of the published works on this. This is not at all new. So back in '96, Paul Kocher targeted something running on MS-DOS, actually an RSA implementation, wrote a paper published on crypto, and managed to extract the secret keys basically remotely from that particular implementation. So we've always known about timing attacks. But I put in some highlights recently. So like it turns out that every 10 years, every new generation of crypto has these vulnerabilities in a different ways. The most dangerous ones are, of course, remote ones, like the ones, because timing is something that you can exploit on a server which is over the internet. So that's very bad, right? If you extract, let's say, the secret key, the secret authentication key of a server remotely. That has been possible quite a few times with even standard middleware like OpenSSL servers. So there's examples from 2003, 2011. And now that we have like a new set of basically signature standards and key establishment standards, the post-quantum crypto coming out, quite a few of those implementations have been also vulnerable to this. So there was, for example, 2 years ago, a full key recovery attack just based on a timing oracle, just based on timing measurements on pretty large class of lattice-based key establishment algorithms. So this is a thing that happens, even if people have always been, throughout my career, have been aware that these things are there. So every generation basically gets to learn the special implementation tricks. So this turns out to be like a part of the craft of a cryptographer. A crypto developer needs to know how to write code specifically to avoid timing attack leakage. So constant time is like a little bit of a misleading term. So what we actually try to do here is to prevent leakage of secret keys specifically. So if your timing depends on something which is public knowledge, like your certificate or something, that's not a problem at all. But if it depends on your secret key, then that might be a problem. So there's basically like three classes of timing leakage. We have like plain old conditionals where, like in Kocher's attack, you would do things depending on a secret key bit. Basically, you would branch here or there, and they would have different latency, and that would leak the key. Then you would have a timing cache attacks, where basically you have some secret address. You are loading, let's say, from a S-box based on your key. And then through many queries, you can extract an AES secret key, because table-based implementations are the most straightforward way of doing AES. Those are basically nowadays completely banned. That was how AES was originally designed to be implemented, was using these table lookups, but you can't do that anymore. You haven't been able to do that for 20 years almost, or since the beginning. And the third class is just instructions that are simply not constant time, like the remainder instruction on most CPUs. Typically, multiplication is constant time, is like a 1 cycle or 5 cycles, but it doesn't depend on the input, or if it's a 1 cycle thing, it doesn't depend on what you are multiplying. It's always the same latency. But remaindering tends to be non-constant time. So doing a remainder with 2 is different from doing a remainder with some larger number. It's just the way it's implemented. Typically, these are assumptions. So when a crypto developer is like working on an ARM or Intel target, they just have these sort of rules of thumb that on most CPUs, you can multiply is constant time, you can divide. And as you can imagine that, like if you're implementing RSA, you have large modular reduction algorithm. So you just have to work around not using division at all during the implementation of that. So one needs to algorithmically transform everything into this constant time operation. So I have some examples here. So for example, if you have a conditional statement like here on the red, which is like, depending on this Boolean S, you have value A or B. You have to be able to like transform it into this sequence of Boolean bit manipulation operations that give you the same end result, but just don't do a branch. And it's a funny art of like tricking the compiler not to optimize that into a branch. So we just hope that the compiler can figure out that it's actually a conditional. So in an interview setting, my colleague, this is actually a question that was, that's one of the interview questions from Chris, my colleague, used here. So symmetric ciphers would have this. They are basic techniques of transforming table lookups into like, let's say, bit slicing operations, so full scan and collect thing. So for example, if you have a table lookup, you have to scan through all of the possible values and then use this sort of bit manipulation magic to extract the value you want, because basically the pattern of addresses accessed by the implementation must not depend on any secret value. So that's a standard trick. So that's why any like production AES implementation, software implementation, runs at like 1/5 of the speed of the fastest implementation out there, just because we are avoiding table lookups because they are so dangerous. This is hugely important. And like I mentioned, division is completely banned. That's why we use special techniques like Montgomery reduction, palette reduction. And then there's let's say, elliptic curve crypto is completely transformed based on this requirement for constant time. It's not the fastest implementation. We want a technique that avoids specifically secret key leakage. So we are not optimizing for speed. We are optimizing most of the time for this particular property. So that is part of the art of crypto dev. But you can see that it's dependent on assumptions that we make about the underlying architecture. So a hardware person who is transforming the ISA into an implementation might not know about our assumptions and just screw it up. And especially with RISC-V, when we have so many people doing independent implementations doing various cores based just on an ISA specification, there's very high risk that few of those don't know about these assumptions that we have, and we will have a non-constant time multiplier, for example. You multiply with 0, that's one cycle. You multiply with something else, it's more. So that would just completely break your OpenSSL stack. It would break basically your remote communication security and authentication mechanisms as well, like locally the authentication you would have. So it's pretty important. So of course, when we implement these and let's say run it on a new system, you need to be able to test it somehow. So one trick that is used often is sort of repurpose various testing methods for use of uninitialized memory. So you basically paint sensitive data, like your secret key, as uninitialized memory, even though it's not. And it turns out that these tools will complain when you are trying to load an address based on an uninitialized address, it will just barf. Or if you are doing branches based on uninitialized variables, it will complain. And that's a way of detecting basically the same sort of error cases that we would have in non-constant time code. But it covers only branches and loads. It doesn't, for example, cover this remaindering operation that we are trying to avoid. So the compiler might still like put a remu instruction in there, and we would be in trouble. We would be leaking information if there's just some clever optimization that a compiler would be doing. But anyway, so these are the production techniques. So it might be surprising that, for example, at Google, when they are doing a boring SSL test, it's really repurposing of wall grind, which is for uninitialized memory checking. And that's kind of the sort of assurance you get. And then, doing like a little timings of the actual operation. Another technique is the memory sanitizer, which is doing pretty much the same thing with LLVM. So this is actually dynamic taint analysis. So it's a kind of symbolic execution. For example, in LLVM, you can there's tools, I think it's called Pitchfork, that you can give it bit code and it will, you can mark certain memory areas as like basically secret, and it will tell you if the bit code compiled from C or Rust or something is trying to branch on that secret variable, or if it's trying to use that as an address directly for loads and stores. So it's a class of vulnerabilities. It has a CWE number also for this. So dynamic taint analysis and forward symbolic execution is something that's usually done on these special intermediate languages like the LLVM bit code, or something that's specifically designed for this purpose. But compilers change things around, so that's not the assembly language. That's not what's being actually executed. But in RISC-V, we actually can do that on instruction set level, so that's a little bit better in my mind. So just a reminder of a few things. So Zkt, this data independent time extension, is part of the scalar crypto extensions that were ratified last year. So in previous RISC-V summit. So we've had scalar crypto out for a while. So it's in some commercial cores. You can buy it from a very prominent RISC-V vendor. It's in compliance suites. Imperas has it. It's in GCC and LLVM toolchains, and recently we have scalar crypto in OpenSSL as well. So scalar crypto is something that exists, and Zkt, this particular specification you'll find in one of the chapters of the scalar crypto spec. Now this also applies to vector crypto, of course. So we are at something like freeze at the moment, I believe. So all of those instructions are also, if you implement those, we expect that, let's say, the vector AES instruction must be data independent latency. There's like some, if you don't implement that, in my mind, you are not like implementing the specification. So this a little, philosophically goes a little bit beyond the traditional ISA contract, which is a purely functional one, which means that basically the instruction defines the arithmetic that you are operating, but here we are expecting that it also means that you are not, that the data doesn't affect the latency at all. The latency can be anything, and it can depend on many other factors, like the location of your instruction in code or something like that. That's fine, but it doesn't need to be the same every time, but it must not depend on the input data in that context. So constant time is a little bit off. So again, we attest that the machine has data-independent execution time for a safe subset of instructions. So this doesn't apply to all instructions, obviously. Your code will still have branches, and of course you need loops. It's not straight line code, but the loops have in your implementation have a fixed number of iterations, so forth. It is the first sort of a side channel ISA contract I know of that exists in any instruction set. It does not affect the functional things. It's kind of exists in parallel to the functional ISA specification. And vendors don't have to implement all of these things to be compliant. So let's say that you don't have the scalar crypto extension. That's fine. You don't have that, but if you can still have constant time extension because you have some subset that we are using in crypto code for this. So the instructions have been selected in a way that we hope that during those data paths which are handling secret information in registers and memory, we would be using only this specific set of instructions during that. So overall management and whatever is going on in your computer, that's fine. But when you are touching secret keys, you would be using these specific instructions. So how do I test it? My personally. So I have a little emulator that I use for this. Traditionally, these are called red and black. So red is something that's secret and black is non-secret in my terminology. I have an entire shadow state of all variables. So variables, you can think of the register set and basically your writable memory as state, right? So in a little microcontroller, that's something that I can double in my emulator and have two copies of that the other copy basically tracks which each let's say byte has an additional bit which says whether or not it's red and black. And then, because we have this taint state, then we can have a set of rules that propagate the red, so that if I do arithmetic on a red variable, basically, then the result will also be red. So it's this sort of tainting logic. It's not, it means that if somehow a secret has been involved in a computation, then the result is also tainted by that secret. And that way we can trace the flow of secrets throughout the process. And if during the execution of a crypto algorithm, if there happens to be a branch that's conditional on a secret, then it's a violation and my emulator will complain. So I'll go briefly through some of the most basic rules here. So for example, load. So RISC-V is a pure load store architecture. So if the RS1 variable here, or the register, is tainted red, you are loading from a secret address, secret dependent address, and that's a complaint. So loads are not on the list, which means that this is a violation of the constant time rule. So if RS1 in these load instructions, the address is a red variable, then it's an alarm. And the rule is also that the destination, whatever you load from there, inherits the status of the memory being pointed here. Because what can also happen is that you are loading a variable which is red, then RD gets that. It's kind of, that's the logic. So if the, let's say, memory address that you are loading, the variable you are loading has already previously been marked as a secret variable, then this register RD will also inherit that. So we are basically tracing the flow of red variables throughout. Same with store, you are pushing the color that happens to be in RS1 into the destination register. So, and then there's an alarm rule, and then these are not on the list, so it's a latency may depend on RS1. Okay. Then more alarm rules, of course, all branches not allowed on red variables. It's a violation if either one of these addresses are red, or these registers are red. Indirect jumps, unconditional jumps. So these basic rules are not actually in the Zkt specification. These are part of my emulator, but this is an approach to variable tainting that seems to be like the only obvious way of tracing the red variables around. Division, yeah, not allowed. It's complaints if your register is painted red. Multiplication is fine. So if RS1 or RS2 are red, that's good. That's fine, because multiplication is constant time. Same with basic arithmetic like addition, XORs, and even these SLTE things, which are actually kind of version of a comparison, that's fine. Shifts, those are all expected to be constant time because we need those for crypto. We really need them. More addition, subtraction, XOR. It's an exhaustive list of these things. Basically so on a constant time list, we don't have the compressed versions of the same things, the load stores and branches, but all of the compressed arithmetic is expected to be constant time, including knob. So we have a fairly exhaustive list here. These are just the implementation things that we did. All crypto-specific instructions are on the list. So forth. So anyway, it runs pretty fast, 10 million instructions per second. So it's like a FPGA target. That emulation speed is close to the actual live target. So you could have this in your continuing integration flow, basically, to test with some test benches, and so forth. Some additional things that need help with instrumentation. You can paint a variable. Of course, there needs to be a method of painting a variable red. So that's a custom instruction that only my custom emulator understands. Also, like setting things back to black. For example, if something is ciphertext, then it's no longer secret. It's already being encrypted, and I can set it to black. That's That's a thought. And of course for testing. So these are custom instructions that only the emulator understands. So I have some examples here, but I'm gonna skip those over. On the margin on the left-hand side, you can see how the emulator actually maps it all the way back to the C source code through a memory map to code lines, so it can complain where this toy AES implementation, for example, is doing addressed or secret-based loads. So the red load, that means that's like bad, and I can I can find the code line that did that from the test bench. Then some technical matters, because there are secret-based branches that are legal in rejection samplers. So this is something that happens in all kinds of crypto. In primarily testing, you are doing, but it's fine as long as you restart the rejection sampling process completely from start and basically discard everything. Those secrets, when you restart, then rejection samplers are fine, but they would create false positives, and then hence you need to instrument around those. But that seems pretty simple. So coming to the conclusion, so we have a timing contract with Zkt. So a like crypto developer like me can now make not guesses, but I'm allowed to do actual assumptions about the instructions, what is constant time, which instructions are not, and which are constant time. Intel and ARM now introduced, actually last summer, I believe, perhaps as a consequence of what we did at RISC-V, introduced some kind of architectural bit which allows a subset of instruction to be constant time. This is, of course, very important for RISC-V because this way we can have something like a Ubuntu, have a shared OpenSSL implementation that can be used across RISC-V cores, and if that OpenSSL implementation plays by the rules and all of the RISC-V cores play by the rules, then that implementation should be secure, which is precisely what we want. I think other emulators should implement this sort of same kind of variable tracing if they are interested in constant time. The instrumentation seems to be fairly easy for symmetric crypto. You just paint the secret key, and then whatever comes out ciphertext, you paint it black, that way one can instrument basically a full binary in a test bench. The actual implementation code externally. So you instrument it before the call to the AES. You basically paint the secret key, and then you perform the call, and then you look at the results if there was a violation during that operation. Yeah, so that's it. That's it. I went a little over time, but it's fine. Yeah.
That was good. So there's one question come from the online audience is any crypto extensions to mitigate fault injection attacks?
Yeah, so that would be a very, very broad contract. So for example, even DPA, like differential power analysis or electromagnetic leakage, the contract would be very complex. Fault attacks would be even so more complex. I don't even know how to define resistance against fault attacks in an ISA contract. I think it is an implementation matter. Fault attacks are there's like a score-based system that is used to measure the resistance to fault attacks. It's a tricky one.
Good. Any question here?
Thanks, Markku. Have you looked at static analysis of identifying this sort of propagating tainting?
Static analysis, well, I mean, dynamic, okay, yeah. It's not quite as powerful, but I've not looked at it to answer your question. I wonder what kind of, what can be said about an implementation using static analysis. It's probably less, I would guess. And anyway, because these implementations are in the end completely straight line code, right? So static analysis and dynamic analysis are pretty much the same thing because the same instructions are always executed. Right?
Okay, so you don't have to worry about being pushed into particular corner cases and
yeah, exactly, because it's the constant time code is always executing the same instruction in the same order. Yeah. So
more questions? No, I think that's it. Thank you very much.
All right, thank you.
Lunchtime.